Hello everybody and welcome to this webinar, wherever you are. My name's Richard Hellebrand. I was trained as a HAZOP leader in the 1990s and have led lots of HAZOPs since, all at upper tier COMA Seveso sites. My job is as Process Safety Superintendent for the Westlake Corporation. I cover the European and Asian chemical plants. Now, HAZOP is the most common tool to identify hazard and operability issues in the process industries. It can be used in projects, for modifications, and to review existing processes. In this webinar, Tuff Rhineland will discuss the origin of HAZOP, the methodology, and some good practice. They'll also discuss potential pitfalls and how AI could be used in the future. Unfortunately, the original webinar on 7th of May failed to record, so unfortunately this is a re-recording of the webinar. Therefore, it will exclude the panel questions and answer sessions we had at the end. Our speakers today, Graeme Laughland and Mahbubur Syed, and myself, Richard Hellebrand. Jake Wynne-Butler isn't present today because he was on the Q&A panel, which didn't get recorded. And before I hand over to TUV, what is HAZOP? Well, there's a little link there you can click on when you see the recording from the IMechE website. It's a systematic method for identifying hazards in a process, conducted in a workshop environment attended by a multidisciplinary team. HAZOP uses a checklist based on parameters and the results of any deviations to those parameters in order to identify hazards within the process and assess how they're managed. The process is broken down into sections, and every deviation to the parameters is considered for each equipment item or step in that section in order to determine what could go wrong. HAZOP's meticulous approach is commonly used with the oil, gas, chemicals and nuclear industries, but the technique can be applied to any appropriate industry or process. And that's enough from me, so now over to UV.
Hello, my name is Graeme Laughland, and may I start by saying thank you to the IMechE for the opportunity to present to you today. I will cover the first part of the presentation. My colleague Mahab will cover the latter part. So who are these guys, I hear you ask? Well, I am a chemical engineer by background and a fellow of the Institution of Chemical Engineers. I am a professional process safety engineer as accredited by the IChemE. And that's probably best described as being akin to being chartered in the field of process safety. I've worked full-time in process safety since the early 1990s. I've worked for 22 years at chemical sites, and these were always upper tier COMA sites. I worked for 11 years at the Nyland Intermediate site at Wilton on Teesside, a facility very similar to FIChemE. Now, the FIChemE disaster was a major incident which occurred in 1974 and was a significant influence on the development of the Seveso Directive and today's COMA regulations in the UK. I've been a process safety consultant for the last 16 years of my career, and that's allowed me to get involved in a variety of industry sectors and operations, from offshore oil and gas, nuclear, petrochemicals, chemicals, pharmaceuticals, power generation, and the water industry. I led my first HAZOP study in 1989, and I've now led over 300 studies. The longest study I led was 34 weeks long, and the shortest one was less than 1 hour. I've led project HAZOPs with more than $1 billion investment. And I've trained hundreds of people on how to lead a HAZOP study and how to be a team member. I've coached and mentored new HAZOP leaders. And I've written HAZOP procedures for clients, and I've audited how companies comply with the HAZOP procedures. So hopefully that gives you some assurance of my competency to speak to you today. Mahab, over to you.
Thank you, Graeme. Good afternoon. My name is Mahbubur Syed. I'd also like to thank the IMechE for giving me the opportunity to present today as well. So I'm a chartered chemical engineer with experience of working in the oil, gas and chemical industries. And this work has included design verification work in feasibility, front-end engineering design and detailed design studies, predominantly in pressure relief. I've also got some experience in process safety, authoring multiple COMA and OBRA reports, as well as carrying out consequence and dispersion modeling. And I have experience working as a technical scribe in hazard studies, LOPAs, so layer protection analysis, as well as fault tree assessments. Thank you. Back to you, Graeme.
Thank you. And this is today's agenda. And in order to make the webinar a little bit more interactive, we also have some poll questions along the way where we can reflect on your answers. So the origin of HAZOP and its evolution. Now, where did HAZOP start and why did it start? Well, HAZOP was originally invented in the late 1960s by a company called ICI. And at one point in time, ICI were the largest manufacturer of chemicals in the UK. HAZOP was originally invented as ICI had experienced some major problems with new large process plant. And it was used at the design stage of a project to identify and correct design faults, which might lead to hazard and operability problems. There are a variety of books that describe the methodology. There's also an IEC standard, IEC 61882, which describes the methodology. And new to the methodology continues to evolve. There is now a Delta HAZOP methodology as published by the FIChemE, and which is used to revalidate an existing HAZOP study. So with regards to the original methodology, ICI's Engineering Services division, known as UTEC, was sold to ABB, and in 2023 to TUV Rhineland Industrial Services Limited, my current employer. Now, TUV currently license the HAZOP study methodology. It's known as EPSHEG 13, and this is the current version of the original ICI methodology. We also license EPSHEG 24, which includes how to conduct a retrospective or revalidation HAZOP of an existing facility. So, HAZOP within the project process, whether it be greenfield, brownfield, or retrospective. Let's look at when and where do we use HAZOP. Today, HAZOP is the most widely used tool within the process industries to review the design of projects and modifications. It is common industry practice to conduct a range of studies as part of a project and as part of the life cycle of a plant. So within TUV, we call these studies hazard studies. And we have a series of studies from a hazard study 0 to hazard study 7. Hazard study 3 is a HAZOP. The hazard study 7 can also be a HAZOP. Hazard studies 0 and 1 are conducted at a very early feasibility or concept stage of a project. Hazard study 2, also known as a hazard, is typically conducted when PFDs are developed, process flow diagrams. A HAZOP is conducted at the detailed design stage when P&IDs are fully developed. And a hazard study 4 and 5 are conducted at the end of construction and at the pre-startup stage. A hazard study 6 is conducted 3 to 6 months after initial operation. A hazard study 7 is conducted every 5 years of the facility's lifetime. So we can conduct a revalidation HAZOP, or we can conduct a retrospective HAZOP where we effectively redo a HAZOP from scratch. Alternatively, we can conduct a process hazard review, or PHR. PHR is another technique invented again by ICI, but this was intended to be used on an existing facilities and not a project. We also license our PHR methodology under EPSHEG 24. So there's lots of terminology within industry used, and this is just a slide to summarize some of that terminology. What's a PHA? Process hazard analysis, that's another acronym that's used, or a process hazard review, a PHR, I hear you say. You know, there's this mix and variety of terminology used within industry. Some companies, especially those in the USA, will use the term process hazard analysis, or PHA. That term, the term PHA, covers some of the hazard study stages, but not all. A hazard study 4 and 5, for example, are a pre-startup safety review, or PSSSR, not to be confused with the pressure system safety regulations in the UK. And again, a PHR is a technique applied at the hazard study 7 stage, and it uses different guide words to that of a HAZOP. Note that many of these studies use either checklists or are a guide word driven methodology. So different tools, different techniques. So typical team membership, who gets involved, I hear you say? Well, this slide summarises typical team makeup for a project HAZOP. And it's key that the HAZOP study leader is independent from the project team. The leader not only needs to know how to apply the HAZOP methodology, but also needs to have the leadership and management skills to get the best out of the team. And believe me, if you have to do a study for 34 weeks, you've got to know your team. In general, we need a mix of safety, design, technical, operations, and maintenance type knowledge. And as a mechanical engineer, you may be required to provide detailed information of the design basis, the maintenance requirements, and information such as the materials of construction. Now, we can also bring in ad hoc team members. I recall conducting a 1 week long HAZOP with 3 representatives from a vendor. By the end of the week, the vendor advised that they'd learned more about their equipment in that 1 week of HAZOP than they'd had in the last 20 years of designing the equipment, because they learned so much from the operations and maintenance staff. So HAZOP is actually a fantastic learning opportunity. Now that brings us to the first poll question. So the first question is, are mechanical engineers invited to join HAZOP studies such that they can make a useful contribution? A, always, B, mostly, but not always, C, occasionally, D, rarely, or E, never. So I'm going to hand you back to Richard.
Hopefully you can see the results there, Graeme.
Yeah. Okay, so the results have come in and they show that generally speaking, mechanical engineers are always or mostly invited to join HAZOP studies such that they can make a useful contribution. So that's around about just over 80%, 16% occasionally. So that's good news. That's the kind of response I was hoping for, actually. So that's great that we are involving people at the right stage. But however, if you're one of those who have never been involved before, put yourself forward and ask to get involved. Okay, so back to the slides here again. So let's talk a little bit more about the methodology. You know, what does the HAZOP methodology actually involve? So, well,
Graeme, I can't see your slides.
Okay. Apologies for that.
Yep, fine.
Yeah, sorry. Yeah. Okay, so what does the HAZOP methodology involve? Well, at this point, I want to remind you that there are books written on this methodology, and I'm going to try and explain the methodology in 7 key steps. First of all, we break the process into nodes. So we typically use P&IDs, break the process into manageable chunks, as we call them, into nodes, and describe the design intent and design limits of a small section of plant. Apply a deviation guide word. Identify causes of a deviation from the design intent. Fourth step is to identify the consequences. Predominantly, we focus on loss of containment events and major operability issues. Step 5, identify and review the protective measures. In other words, review the risk. The risk assessment can be qualitative or it can involve use of your company risk matrix. Step 6 is to, where necessary, develop recommendations to take action to address the identified risk. Finally, we want to make sure we record the study as we've got to repeat this methodology by going on to the next guide word and the next node and iterate round this methodology quite repeatedly until we've reviewed all the guide words and then repeat this process for each node. So that's a very, very brief summary of the methodology. Now let's discuss each step in a little bit more detail. So in terms of node markup, what is a node? Typically in preparation for the study, the HAZOP leader will review the P&IDs and break the process down into relatively small chunks. We like to call them manageable chunks, and there is an optimum type size for a node. Effectively, if you have a greenfield project where you're building a new plant, then all the pipework and equipment shown in your P&IDs will be coloured in such that they belong to a node. That's one way to help ensure that you cover everything. So what happens at the start and the end of the process, I hear you say? Well, you do need to consider interfaces with raw material and utility suppliers, and with customers in the environment, whether this involves effluent discharge or atmospheric emissions. What are the guide words and how do these get used? Well, if I refer you to IEC 61882, there are a range of guide words, and these are described as basic guide words, such as no, more, less, reverse, as shown on the left-hand side of the screen there. These are typically combined with a process parameter, such as flow, level, pressure, temperature, something that we're measuring typically, to give a deviation guide word such as no flow, more level, more pressure, less temperature. Then there are sequence or batch guide words such as early or after. You know, if you've got a heater in your process, the heater could be switched on too early. Or if you've got an agitator, the agitator could be started after the catalyst is added. So these are the deviations that we'll look to examine. Then there are non-specific guide words such as access and maintenance, which allow you to consider these aspects of design and whether or not they present some safety or operability issue. And finally, IEC 61882 talks about using a common sense checklist at the end of each node to help raise any outstanding issues. We use the guide word other to capture any remaining thoughts posed by the team. That takes us on to poll question number 2. So poll question number 2 is, prior to being involved in your first HAZOP study, had you received any formal training? And it's a simple yes or no question. So again, I'll hand you back to Richard.
And there's your results.
So here we are. And well, quite surprisingly, only 18% of people have received formal training in the HAZOP study methodology prior to attending the first HAZOP study. So if you're one of those people who have yet to receive training, I suggest put yourself forward to get some formal training. It can only help enhance your competency so that you can make a good, effective contribution to these studies going forward. And then back to the slides. So the next part of the methodology is to look at identifying causes of a deviation. And this is where the team brainstorm all possible causes of a deviation. And a lot of teams start with no flow. Well, you don't have to. For example, if temperature is what is being controlled in the node, I would tend to start with more and less temperature as deviation guide words. And sometimes going for the very obvious deviations just can help get the team started and off and running. So a very useful tip when looking at causes, most often, and I find that initiating causes are either an equipment failure or a human error. So as shown in the slide there, you know, an equipment failure is like a temperature control loop failing such that the valve goes wide open, or a human error might be a manual valve being left closed on the discharge of a pump when switching product lines. Now, it's very important to ignore protective systems at this stage. Okay. Next step is to identify immediate and ultimate consequences. And a major failing of many HAZOP teams is to only consider the immediate consequence, e.g. the team stops the description of the consequences with vessel overfill, or worse still, demand on high level trip. So this is only part of the story. We really need to understand the ultimate consequences. Could someone be killed, for example? It's only by understanding the severity of the outcome of a loss of containment event that we can truly look at providing the most appropriate safeguards. And certainly when I look at some older HAZOP studies, this was a major failing of those studies. Next, we need to look at our safeguards. We need to identify and review the protective measures. Now, what safeguards are there in place in the design? So it's best to think of the safeguards in the order in which the safeguards come into play. There's a logical hierarchy such as alarm, trip, pressure relief valve. We should also think of both preventative and mitigative safeguards. Now, when a loss of containment happens, how will we know that this has happened? Will it take seconds, minutes, or hours to detect or observe a loss of containment? Now, will an operator observe a leak? Will gas detectors go into alarm? Will spillages be detected by effluent analysis? Or is it once someone's injured that we actually discover something's wrong? Then we then need to test the adequacy of the safeguards provided. And by test, we can either recommend some quantitative risk assessment, such as a LOPA, layer of protection analysis, or a faulty analysis, or we can make a qualitative or risk-based judgment that the risk has been adequately controlled. And we can do that by asking, are we meeting relevant good practice? And asking what more could be done and why are we not doing it? So, and then finally, in terms of recording, this is just one example way of recording the HAZOP notes, and this is an example entry that's used a company's risk matrix. So you can see here it's been used to help define the severity of the event and put a likelihood and hence the risk of the event happening. Now, in line with COMA report updates under company standards, we must revalidate such studies every 5 years. So it's important for the HAZOP record to be readily understandable. Take care and time to record it so you can understand it in 5 years' time when you read it back. Because another key part is the revalidation of these studies. Now, this flowchart shows a decision tree that you should follow to determine if a HAZOP study should be redone or revalidated. And typically on a 5-yearly basis. You can get more information on this type of HAZOP study by reading the Centre for Chemical Process Safety, the CCPS book, entitled Revalidating a Process Hazard Analysis. Now, in practice, most often poor quality studies need to be redone. And in the long run, it pays to have a quality study done the first time around so that you can simply update the record and revalidate it in the simplest way. So what do we mean by quality HAZOP records? Well, here's some really good guidance on poor and good practice recording. Best practice is to explain in some detail which specific valve is being discussed and why a valve may be left closed in an error. The consequence description needs to explain the ultimate consequence. So tell the story of how the hazardous event unfolds. Explain how it happens in a sequential manner. And in terms of safeguards, list them in the order that they come into play. And that helps us think of reality and helps make sure that we have thought of all the relevant safeguards where we've got them. It's important we don't overlook safeguards that we do actually have. And where appropriate, we will highlight where there's a lack of independence, for example, if an alarm and trip, which may use the same sensor, because that may suggest we want to do something about that. That brings us on to poll question number 3. And this is asking, are HAZOP studies a useful mechanism to identify and raise asset integrity issues?
Okay, and here are the results.
So quite clearly, a very strong supportive message there saying that HAZOP studies are a very useful mechanism to identify and raise asset integrity issues. But of course, they're not the only tool that you can use to do that, but certainly a very useful way to get issues highlighted. So back to the slides again. Pitfalls. Where can we go wrong in a HAZOP? Well, there's a whole list of things here. We could fail to conduct earlier studies. As mentioned earlier, for projects, HAZOP is just one stage of a series of HAZOP studies. And typically there are studies such as HAZOD or HAZOP Study 2 conducted prior to conducting a HAZOP. Now we know that in the UK, the HSE have actually prosecuted a company for not having undertaken such studies. Lack of planning, adequate resourcing. A failure to plan the timing of a HAZOP study or provide adequate resourcing in terms of a budget can potentially lead to studies being rushed or poor quality studies being undertaken. We have had to redo an entire plant's HAZOP following a major incident, and this took several months, but the site manager would not restart the plant until a good quality HAZOP study was done. That's quite an extreme measure, but it has happened. Poor preparation. Preparation should be done ahead of time. It's much more efficient if a small sub-team is formed to do the preparation. Typically, the leader, the scribe, the lead project engineer can develop the notes, gather relevant information about each node, and do as much preparation as possible without the whole team, as it's much more efficient. The composition of the team is very important, so carefully select the right team. We often say the three most important things about HAZOP are 1, the team, 2, the team, and 3, the team. Node size. Select the optimum node size. Too large and things will get missed. Too small and the study can become overly repetitive and the team switches off. Having accurate information. Be sure to know which version of the design you're actually studying. One of our clients had 3 different versions of a cause and effect matrix, which begs the question, which is the master and which is the correct version? And be sure that you can readily access information, the information that you'll need. For example, you may need access to your maintenance database in SAP or Maximo, so be prepared to contribute to the study and come prepared. HAZOP, by its very nature, it effectively assumes that the design will work. Well, you know, if something doesn't look right, say so. Once led a study where the absence of one valve would not allow startup of an offshore platform. Fortunately, this was identified during the HAZOP. Lengthy arguments. Well, the leader needs to control discussion and be able to work with the team to resolve issues. Raise a recommendation to address any uncertainty and move on. Experience can bias the team. Well, whilst experience is beneficial, does a team member's input really stack up? Are we able to provide suitable justification for information provided? If in doubt, seek some further explanation or raise a recommendation. Next is Shanahan's law. Well, the length of a meeting is proportional to the square of the number of people present. Are there too many people involved? Some who are making no contribution or some who are causing distraction to the rest of the team with side conversations. So who is actually an essential team member and why? Poor team engagement. Are all team members actively engaging with the study? In particular, with online studies, a good HAZOP leader will seek input from each individual. Address them by name. Design in the meeting. Avoid spending excessive time redesigning the project in the HAZOP meeting. A good HAZOP leader will stop this, but it's often a common trap. Poorly worded recommendations. Would the recommendations make sense in 2 or 3 weeks' time after the study is completed? Are they ambiguous? Do they stand alone? Is it clear what is being asked for? Why is it necessary and where does it apply? So think very carefully about the wording of your recommendations. Other pitfalls. When we compare and contrast projects versus existing facility HAZOPs, there's quite a difference here. So a HAZOP, a retrospective HAZOP, is a HAZOP conducted on an operating plant, which may be 5, 10, 15, 20, 30 or more years old. A project HAZOP team is typically a larger team, as it will include EPC design contractors involved in the design as well as operating company representatives, quite often someone from each discipline from both the APC and the operating company. For a retrospective HAZOP, it can be a challenge to get the availability of operations engineers. They have an operating plan to support. So it is difficult. P&IDs for a project HAZOP will have the P&IDs been subject to a design review in line with IEC 61160. Are they truly ready to be HAZOPed? For a retrospective HAZOP, are the P&IDs as built or have modifications taken place and which are not reflective of what is in the field? In terms of design knowledge, for a project HAZOP, the designer will likely be present in the HAZOP study, which is great. But for a retrospective HAZOP, do the engineers really understand the basis of design? When it comes to vendors, for a project HAZOP, the vendors are likely to be present in the HAZOP study. But for a retrospective HAZOP, do the vendors still actually exist? In terms of incidents, for a project HAZOP, no incidents will have occurred on a facility yet to be built, but as someone research incidents that have happened in similar plants elsewhere in the world. And for a retrospective HAZOP, is someone providing input on the actual incidents that have occurred on the plant? When it comes to change control, when does management of change control take effect within the project? Does the project team know this? Does the project team follow the management change procedures? And for a retrospective HAZOP, have the management change procedures been followed on the operating plan? Is there evidence of changes in the field? With regards to recommendations, for project HAZOPs, have the HAZOP recommendations been addressed and addressed as originally intended? Has the identified risk been addressed before the project is started up? For retrospective HAZOPs, is there available resource to address the recommendations that the study team have come up with, or are they being addressed in a timely manner? When it comes to human factors, for project HAZOPs, are the teams suitably competent in relation to how human factors should be addressed? Are designers developing designs that are error prone? Can human error be made less likely or eliminated? Best of all, for retrospective HAZOPs, again, are the teams suitably competent to identify existing human factor issues that promote human error? Have incidents revealed shortcomings? The first plant where I worked at in Northern Ireland, there was an operator called Vaso. Not a traditional Irish name, you might think. Well, he was called Vaso because he was the only operator who tried to make a batch of product without the catalyst, which was called Vaso. So, mechanical engineers, what's your part? How do you participate in a HAZOP? Well, as a mechanical engineer, do you understand the design and how the process is supposed to function? Do you understand the basis of safety? What scenarios pressure relief and trips have been provided for? Do you understand potential integrity threats to the plant? Do you have good knowledge of relevant good practice publications, for example, API RP521 for pressure relief, or HSG 244 for the provision of ROSOFs, or any internal company standards that stipulate requirements for safe isolation? Do you have knowledge of or access to the design and operating limits? Where will you find these? Are you able to clearly describe the integrity issues that present a loss of containment threat to the process? For example, causes of internal corrosion. Is corrosion under insulation a threat? Microbial-induced corrosion, dead leg corrosion. Do you have an appreciation of the type of hazard that can arise from a loss of containment? The size and magnitude of potential releases, a jet fire, a flash fire, a vapor cloud explosion. Do you have ready access to test and inspection records to confirm that critical equipment is actually being suitably maintained? Do you have knowledge of incidents on the assets that you're responsible for, and for similar assets elsewhere, either within your company or outside your company? And are you aware of changes that have occurred within the project or to an existing asset? So quite a lot to think about there, but finally, please be participative. The three most important things about a successful HAZOP are 1, the team, 2, the team, and 3, the team. That brings us on to poll question number 4. in relation to critical equipment, could HAZOP studies make a stronger link to asset integrity programs, in particular in relation to major accident hazard scenarios and the identification of safety critical equipment?
And here are the results.
Okay, so I think quite clearly strong support for the answer yes. Yes, HAZOP studies could make a stronger link to asset integrity programs, in particular in relation to the major accident hazard scenarios and the identification of safety critical equipment. And I think mechanical engineers have a role here to play and being participative in these HAZOP studies to make sure that link does exist. So something to reflect upon there. Thanks. Back to the slides. Okay, and sorry, beg your pardon. It's now over to Mahib.
Cheers, Graeme. Thank you.
Yeah, sorry.
Thank you, Graeme. So as Graeme mentioned previously, I'll be discussing how AI augmentation can be integrated within the process industries, specifically in risk-based type studies, such as HAZOP, and what that might mean for us as engineers, especially those of you from our mechanical background. Before I start, we'll have a look at this poll question that we previously did. Do you think AI should be used to support hazard studies? A, yes, it can improve efficiency and consistency. B, maybe, but only if it's properly supervised. C, no, HAZOPs rely too much on human judgment. Or D, I'm not sure. You'd like to learn a bit more first. So if I just pass over to Richard to look at the answers.
And here they are.
So 60% said maybe, but only if it's properly supervised, which I expect the majority to have said. And only a small minority said no, HAZOPs rely too much on human judgment. So hopefully I can sway the minds of those. Just take the screen share again. So why AI and HAZOPs? So why are we thinking about introducing AI functionality into HAZOP studies? There's some generic pain points listed on the slide here, and I want to talk about how AI can help us with these. So it's not just the HAZOP session itself that takes time. A lot of effort actually happens before anyone steps into the room. So first there's loading up the PNIDs. Then you've got to set up the relevant workbook or software you're using for the HAZOP to record the discussions. You have to apply the risk matrix and relevant guide words. And it's a huge opportunity for AI to help, whether that's suggesting node boundaries based on system layout, maybe auto-generating templates, or even pre-filling some common failure mechanisms and safeguards. So we talk about the HAZOP session itself. AI can be trained on past HAZOP data, process safety reports, and even equipment manuals. So when a deviation is raised, such as high pressure, it might be able to suggest likely causes specific to that node. For example, a blocked outlet, a failed pressure control valve, or inadvertent upstream valve closure. It can also suggest likely consequences based on process context, such as overpressure of a vessel or loss of containment downstream. AI has the capability of scanning PNID drawings and tagging existing protection layers, or such as PSVs, alarms, interlocks, double block valves, and help the team assess whether safeguards are in place and correctly documented. It might even flag missing safeguards or check whether those safeguards have been effective in past studies. Based on the discussion, AI can propose typical follow-up actions, such as relief valve size and verification, any SIL reviews, or inspection of equipment conditions. And this will pull from a database of common recommendations. So this doesn't replace expert judgment, but it does help the team move faster. It can reduce the likelihood of missed items and then stay consistent with best practices as well. Once the HAZOP session wraps up, we can think about now writing the report and compiling this data. This is usually where momentum slows down. So the scribes and engineers are left with a massive spreadsheet, scattered notes, maybe some unclear action items, and now they have to turn that into a clear, well-structured report for management, regulators, or even clients. AI can take the structured data from the HAZOP spreadsheet and automatically generate a draft report, complete with node summaries, key findings, outstanding actions, and even risk ranking tables. It can standardize the language and formatting, so we don't have to worry about typos, any inconsistent phrasing, or even any copy and pasting errors across 30 plus pages. So what's the problems with AI? Why did the small minority say they didn't want to rely on AI? So we've talked about how AI can do, but in reality, not everyone might be comfortable handing over parts of a safety critical process to something like AI. Firstly, HAZOPs rely heavily on human judgment. So engineers don't just follow our template, we rely on our experience, our intuition, and cross-discipline discussion. And there's a fear that AI might oversimplify that, or worse, miss something critical. The second point is trust and accountability, which are big concerns. So if AI suggests a consequence or a safeguard, who's responsible if it's wrong? People worry about black box decisions or recommendations without any clear reasoning. The data that AI learns from might be incomplete or biased. If it's trained only on past projects, AI might miss novel hazards in new technologies or non-standard designs, such as in the new battery technology industries. In terms of the mechanical aspects, mechanical engineers might often ask, can AI really understand the equipment? Can it distinguish between a centrifugal pump and a diaphragm pump in the context of a HAZOP? Does it understand how a double block and bleed setup actually works in the field? Then we have the human factor. Some worry that AI might reduce team engagement. If we rely on prompts too much, will people stop challenging each other or thinking deeply and outside about scenarios? And then finally, we need to involve the relevant regulatory body, such as the HSE. The HAZOP is a core component of process safety risk management. Regulatory bodies need to ensure that companies are following robust, proven methodologies. If AI modifies or influences the process, then this must be scrutinized. So with all that in mind, how should we as engineers actually go out about implementing AI in HAZOPs? Well, the key is to take a measured engineering-led approach, just like we do with any new technology or system that affects safety. We don't need to throw AI directly into a live study on day one. We can start by trialing it in low-risk areas, maybe use it to generate draft HAZOP templates or pre-populate common deviations, and then we can validate those outputs against our expert judgments. We need to make it clear who's accountable for each decision. So AI might suggest a safeguard, but in general, it's the team who reviews and accepts or rejects it. This will keep the confidence high and avoids that kind of black box effect that we were talking about. The more feedback we give AI systems, i.e., what worked, what didn't work, the better that it will get. So it's like a continuous improvement process, just like anything else in engineering. AI works best when it has access to insights from all parts of the team, be it process, mechanical, CNI, operations, etc. And that collaboration becomes even more powerful when supported by good tools. So in short, we don't want to treat AI as a shortcut. We want to treat it as a tool to help us do better engineering faster and more consistently, with us as engineers still being the focal point. So I just want to talk a bit about this project we're working at TUV Rhineland, which is introducing AI augmentation in HAZOP studies. So there are three main aspects of a HAZOP study that we personally think AI could potentially help with. So these are pre-population of design limits. As I mentioned, AI has a capability to read design documentation and read relevant information from them and pre-populate these. We're also looking to use AI to standardize safeguards for a more consistent approach to HAZOPs. And we're also looking at the capability of automated report generation. So essentially, this project stemmed from a previous project, which was the implementation of AI for use in risk-based inspection studies. And we currently have an RBI tool at TUV Rhineland, which automatically extracts engineering data from design documentation such as P&IDs, data sheets, etc., and pre-populates the system. And then there's some human verification of that data following this. So this removes the need for manual entry of the data. It speeds the time a lot, makes it a lot more efficient in terms of running RBIs. The AI looks at construction, design, and operating conditions, as well as the inspection history of that equipment, to then produce a written scheme of examination. And it also outputs recommendations, and this is to understand when, where, and how frequently to inspect the equipment. The RBI tool compares the data against 20 years of records, which is good for benchmarking to ensure that there's that consistent approach. So it's important to be aware that there is always a human verification step as AI is pre-populating this data and producing outputs, similar to what we want to implement in this augmentation for HAZOP studies. So that concludes my section on AI augmentation. I'll pass back to Richard now to close out.
Okay, I really want to thank both of you. This is the second time round for both of you delivering this presentation. The first time round, we finished off with the Q&A. It was very lively. Questions continued to come in after the event, and it was one of our most popularly attended webinars. So there's clearly an appetite for everything to do with HAZOP, certainly amongst mechanical engineers. And if you come across this on YouTube, then again, you'll see the quality of it. We got a lot of advice about best practice and how to do things, but also a lot of thought-provoking ideas about what's next. And it's not a static topic. If you've been involved with HAZOP for any time, it used to start off with old-fashioned word tables, and now it's moved on, and there's sophisticated software. And fortunately or unfortunately, the march of AI is never ending. Just before I finish off, just to remind you that not only this recording will be on YouTube, but you'll find there's actually a lot more. We have an active process industries division in IMechE. We try and run events, webinars, and even physical events throughout the year, typically sort of 15 to 20 events per year on topics that are interesting. We hope they're interesting. Everyone who does these things are volunteers. If you want topics that you don't think are being covered, contact us, give us some feedback. We'll try and lay something on for you. If you want to get involved, that's even better. I'll put the final slide up, and I'll just leave this up here. Even if you've come to this one late, then there is a feedback form, and you could ask for a CPD certificate. Now the CPD certificates are not a qualification to do HAZOP, right? This is just an hour or so of interesting information. Do not dare go off to a HAZOP and say you've been trained after this one. But hopefully it'll prompt you to get some more training if you need it. If you want to talk about HAZOP, for IMechE, I'm sort of doing quite a lot on process safety. My email address is up there, richard.hellebrand@member.imeche.org. I'm happy to get into a conversation or get other people involved in the conversation. So at that point, again, thank you very much for both our speakers. Apologies to Jake, you were on the original Q&A panel, you're not here now. But hey, life's not perfect. So thank you very much, everybody. I'm just going to leave this slide up for a couple of seconds in case you're on YouTube and you want to jot down that email address. But I will then stop recording and basically I think I'll stop now because I think we've had enough. Thank you.